as well as in Mainz, China, Korea, Switzerland, Hayward, and various other distinguished cities. He'll tell us today about his fundamental physics with weird magnetic resonances.
Mike, maybe I don't. No. Does it work? Let's see. No. Let's try this. Okay, in case you're wondering what these pictures are, these are cartoons by Bruno Duszek that I snapped on my cell phone during a recent visit to Frascati. And the reason I'm showing them here because I think they're relevant to what I'm going to say. Anyway, there are a couple of closely related stories that I would like to tell you today, and I have to stay focused in order to be in time. So let's begin. Magnetic resonance talks are impossible without mentioning Erwin Hahn. And all of us here were extremely lucky to have him as a colleague for many years. And I would like to remember that one of the things we've done together with Erwin, I think it was about 2005, we were asked to give a lecture on physics of music, maybe in this very room. I don't know, it looks like it, right? And so what we did is, with the help of our very able demonstration people, we filled the room with all kinds of things like this violin playing machine, Helmholtz resonator, this wave machine and whatnot, and we wrote a scenario how this is going to be. And the first thing during the lecture was that I was going to introduce that Professor Erwin Hahn will now explain what sound and waves is. And so Erwin comes out, and there's an audience of the public, parents, children, and everybody, and says the following. He says, "I feel a little bit like a mosquito at the nudist beach." And the people look at him, and he said, "I don't know where to start." But, okay, anyway, I do know where to start. And this will be with searching for ultralight dark matter with nuclear magnetic resonance. So before I get to that, I have to say a few words about dark matter. And I believe every other talk, every other colloquium talk mentions dark matter and talks about it in some way or another. And we all know that there is a big problem in physics that we don't know what most of the matter is. We have multiple evidence that there is something out there, and this evidence comes from, for example, from the fact that stars in galaxies are not moving with the speed that we would expect from Kepler's laws, and galaxy clusters are moving in a funny way, and on and on and on. But we don't know what it is. And for many years, people have speculated what this might be. And I made a little list here about what the candidates are. Well, the first idea about this is that maybe it's not actually matter, but maybe it's just that we don't understand gravity. In fact, our knowledge of gravity mostly comes from sort of a planetary scale where we measure the orbits very precisely. But what if we go to a larger scale, like galactic scale, and gravity fails? The problem with that is that dark matter is not a galactic problem. It appears on all kinds of scales, all the way to the whole universe. And how can you modify the laws of gravity to explain everything? And in fact, it's hard. And so various attempts to do this, like modified Newtonian dynamics, they have problems. Nevertheless, people are really trying to do this. And this is still an active area. Then there is another idea that so far only applies to galaxies, a very recent one that says that actually if a photon has a tiny mass, then electrodynamics has to be modified, the plasma equations have to be modified, and maybe that can explain the forces in the galaxy. I'm actually sort of a little bit involved in this one, and if you want to know more about it, I can tell you about it later, but it's not the topic today. Then people thought that maybe black holes, dark planets, interstellar gas, or like Rich Muller says, bricks. But I think there is a very strong evidence that bricks are not dark matter. In fact, for example, when clusters of galaxies collide, then we see that the dark matter interacts very weakly with normal matter with itself, so bricks wouldn't cut it. So there's a sad face here. Now, still, probably one of the best motivated candidates that people, including people in this very department, are so ably looking for is something called weakly interacting massive particles that are particles of, say, GeV, maybe 100 GeV, something like that scale, and you look for them with methods that we usually use in particle physics, by collisions of these particles. And they're weakly interacting, so the cross sections are very small, so it's very hard. But it's still a good candidate. But recently, a whole other class of candidates for dark matter has emerged, and this is so-called ultralight bosonic particles. And there are many different varieties of these things, like axions, which are pseudoscalar particles, meaning that the spin is zero and the intrinsic parity is minus. Some generalization of these called ALPS, axion-like particles. There are also scalars that come out in some string theory. These are called dilatons. Some vector particles, such as dark photon, for example, and tensor particles, and so on. And I'm actually involved in searches for all these guys, but today I'm going to limit myself somewhat to some of these things. Now, I should confess that I've only been working in this field for a small number of years, and as I was learning this field, all of a sudden it struck me a very, very simple but very interesting, in my opinion, fact that even though we have no idea what dark matter is, like sleuth, we can make a little card and say we don't know who this is, but we still know a lot of things about it. This all starts with the fact that by actually looking at these rotation curves in the galaxies and assuming that it is dark matter, after all, we can estimate the density of dark matter in the galaxy. And for our galaxy, it's something like 0.4 GeV per centimeter cubed, which means that it's about 1 proton per 3 cubic centimeters, something like that, which is a very, very tiny density compared to this table, but turns out dominant thing in the galaxy nevertheless. Okay, so we know what the density is, and the second observation we make is also absolutely trivial, that these particles, in order to be confined to galaxies, and we see experimentally that there is it looks like galaxies have halo of dark matter, but they don't, this dark matter is associated with galaxies. It means that these particles have to move slower than the escape velocity. So this laser pointer goes up and down, but if I toss it up very fast, and if there was no ceiling, it would escape, right? So in the same way, dark matter moving faster than about 10 to minus 3 speed of light would just escape. So if we immediately see that whatever we are dealing with here is deeply non-relativistic. This should be a relief to people trying to pass an exam. Okay, non-relativistic. Anyway, non-relativistic. So this list can be continued. So, for instance, if we assume somehow that the mass of a particle is less than about 20 electron volt, we can say that it has to be a boson. It cannot be a fermion. Why? What dark matter? How can boson fermion? How come? Very easy, because we have the density, we have the mass of the particle, we can find the density, number density of particles by dividing one number by the other. And if it is fermion, there is Fermi velocity, so we can calculate Fermi velocity, and it better be smaller than 10 to minus 3c, otherwise dark matter goes out. So if dark matter is lighter than 20 electron volts, it has to be a boson. Amazing. Then, if we are talking about a large number of bosonic particles with large density, maybe talking and thinking about these things as individual particles is not so convenient. Maybe we should think about it sort of like some field, like we can talk about photons, but in some cases it's better to think about electric and magnetic fields. So then we can think about this bosonic oscillator and the fact that they move very slowly. The total energy of such a bosonic oscillator would be the mass plus kinetic mc squared, right, plus kinetic energy. And this kinetic energy is about this. In other words, this bosonic oscillator has a Q factor of 10 to the 6. The other thing we can add to this list is that the particle cannot be lighter than 10 to minus 22 or so electron volt. You know why? Because it's confined to the galaxy, and if it is lighter than the de Broglie wavelengths of this thing, will be larger than the galaxy. So it better be heavier than that. So a lot of things we can say without ever knowing what dark matter is. So I find it really fascinating. Some people think it's a Bose-Einstein condensate, but it's under debate, actually. So axions was number one of my list, and so axion, you know, sounds like pion, muon, axion, right? And in fact, Frank Wilczek, in his Nobel lecture, when he was describing how he came up with the name of the axion, he said, yes, it sounded scientific, but actually it was named after a cleaning fluid. And the reason it was named after cleaning fluid is because introduction of axion had nothing to do with dark matter problem at that time. It was introduced in order to help understand the so-called strong CP problem. And in simple language, the idea is that there are strong interactions that are described by quantum chromodynamics, and there is a place in quantum chromodynamic theory where you can very easily introduce CP violation. There is a parameter called theta parameter that could be anything from 0 to 2 pi in principle, but from experiments, actually because electric dipole moment of the neutron specifically is very small, despite the fact people are looking for it for many, many years, they haven't found it, and that sets the limit on this parameter of less than 10 to minus 10 or so. So it must be some really, really fine tuning, and it looks unnatural to theorists, and so this axion particle was introduced, which made it not an accident, but a systematic phenomenon why this theta should be close to 0. And only many years after that, people realized that this is also an excellent candidate for dark matter, but once we are at it, why not dark energy potentially? And also because the physics of the axion is closely related to CP violation, maybe this will also, when we find it, tell us something about baryon asymmetry of the universe. And these two gentlemen here in the front row made a big splash about a year ago, I think, when they also proposed that hierarchy can be explained with axion, and hierarchy is this annoying problem that the natural scales of physics are very large. Energy scales are 10 to the 16 to 10 to the 19 GeV, and all particles are 100 GeV or less So how can this be? And this is the hierarchy problem, and again explain. So maybe axions can solve all your problems, and so they are very well motivated to search for. But how do we search for them? Well, first of all, you might say, we don't need to search for it, we already found it. Because we see that it's, if we assume that it's dark matter, it's there, so what do you mean search for it? Well, what it means is that we need some other interaction to detect them. And we consult Surjit and our mutual friend Peter Graham, who are the laureates of this year's New Horizon Prize in Physics. Congratulations again. And they tell us that in addition to gravity, the axion can interact only in three plausible ways. So one of them is the interaction with the electromagnetic field. And let me explain what these letters are here. So from now on, I'm not going to talk very much about axion as a particle. I'm going to assume that there is this axion field around us. And I'm going to designate this with letter A, the strength of the field. And this is the electromagnetic tensor. So this is the interaction of axion with photons. Similarly, there is an interaction with gluons, and this interaction is responsible for the electric dipole moments, and this is the reason this interaction is why the axion was introduced. And I should say that most current searches for axion are based on this interaction, axion-photon interaction. But our CASPEr electric experiment that I'm going to describe shortly is looking for this. And there is another interaction that is called derivative interaction. And the reason it's called derivative interaction is because instead of the field itself, there is a derivative here multiplied by this fermionic current. Now, this is the relativistic notation. If you simplify it to the non-relativistic form, this is just going to be spin. And this is a gradient of a scalar, which is a vector. So it's some vector times the spin. So basically what it is an effective magnetic field. It's an interaction like magnetic field interaction, and we look for it, and other people look for it. I'm going to tell you about it shortly. So actually, I'm going to tell you about it now. So this experiment is called Cosmic Axion Spin Precession Experiment, and I think around 2000, I forgot, 2013 or 2012 or something, Peter Graham and Surjit Rajendran showed up in my office and said, we would like to really find an axion in some new ways, and we would like to discuss with you some experimental schemes. And they had some idea that I helped them get discouraged about, and then we talked for several hours, and at the end of this, Surjit will confirm this, I told them, guys, I would like to congratulate you, because this afternoon we invented NMR. Because this experiment looks just like NMR. And by the way, it is really complementary to other experiments. For instance, this great flagship experiment in Seattle called ADMX, where John Clark is one of the key participants as well. And many others. Maybe I'll tell you about those experiments. So we look at typically at lower frequencies. Anyway, before I get to tell you how this is just like NMR, the key ideas for the CASPEr experiment is that, okay, so we're talking about this bosonic field consisting of many axions, and the equations, Klein-Gordon equation tells us that it has to oscillate in time at the frequency equal to its mass. And in our experiment, we actually, this is now outdated, it's now from microhertz gigahertz that we are looking at. This interaction with gluons that I mentioned will lead to CP violating nuclear moments such as electric dipole moment and shift moment and so on. And we look for this in the version of the experiment that's called CASPEr electric. The derivative interaction, which is this quasi-magnetic interaction, we'll look at the CASPEr lead. So we have two sort of big branches of this experiment. And just to remind you that we're talking about this oscillator Q factor of about 10 to the 6th. So the reason this is important because it's going to be a resonance search, and the widths, relative widths of the resonance will be fairly narrow. So how did we invent NMR, so to say? So this is how normal NMR looks like. So you prepare spins somehow polarized collinearly with an external field. It's called a leading field. And then you come in with another field, usually perpendicular to that one, which is very weak typically compared to the main field. And if this field is, the frequency of oscillation of that field is non-resonant, has very little effect on the spins. However, if you keep the Larmor resonance, so that is the frequency with which a spin precesses around the leading field, then the NMR magic happens and these spins start to rotate away from the axis. So what we do is we replace this additional oscillating magnetic field with something related to axions. And there are two versions of the experiment, as I mentioned, electric and wind. In the wind experiment, we just rely on the gradient, which is also the velocity of the axions. And it's oscillating, so it produces exactly the same effect as the oscillating field. When we are looking for the electric interaction, then we apply a strong static electric field, and the dipole moment that oscillates then creates an interaction that also looks like an oscillating magnetic field. So exactly like the NMR. And that's why I said that we invented NMR. And then we would get the spins that are initially polarized along the magnetic field to perform a motion like this. And we can pick up this precession, for example, with a squid magnetometer. Now, it turns out that what sample we choose strongly depends on which one of the two experiments we are doing. And so these experiments sort of optimize in different directions. So for the wind experiment, we chose hyperpolarized liquid xenon, which has a property that the coherence times are long and we can have a lot of it. And for the case of the electric experiment, we chose a ferroelectric material where there is a strong intrinsic field that we can use, much stronger than any field we can dream of applying directly outside. Anyway, so these two experiments are being set up. I have a lot of pictures, but I'm not going to show you too many. This is just one. This is a giant xenon hyperpolarizing machine with all kinds of beautiful glasswork and a 100-watt laser for pumping rubidium atoms that then collide with xenon atoms and transfer the polarization to xenon atoms and so on and so forth. So this experiment is being built at the moment. The electric experiment is headquartered at the Boston University and is spearheaded by Alex Sushkov, who is actually my former PhD student who graduated from this department some years ago. And this picture you see his current graduate student Denise Ibas and my student Alex Wilczewski. And this guy here is wearing very important message on the T-shirt that said that safety is a part of science. I think EHNS here gave us all such T-shirts and they come handy. Anyway, this is the CASPEr electric experiment. And then I'm going to flash how people usually present sort of the sensitivity of such experiments. So these are different coupling. The three couplings that I mentioned, this is the axion-photon coupling, this is the axion-gluon coupling, and this is the derivative coupling. And then what you typically have is the mass of the axion here, and the strength of the interaction in some units is plotted here, and then you draw various projections. I don't like these plots very much, so we'll move on. They're useful, but you might ask, why don't I like them? It's because they mix results and projections, and I feel not so comfortable. Anyway, yeah. Actually, now I want to leave that dark matter story for a few minutes and tell you another story, and then we'll come back together in a little bit. And the story I want to tell you now is about NMR without magnets or coils. And actually, I heard about this strange kind of NMR for the first time from John Clark many, many years ago. It was very fascinating, but I had nothing to do with it myself until Professor Alex Pines from the chemistry department and his then postdoc Andreas Trebesinger, who then later became one of the founding editors of Nature Physics. We may have gotten rejections from him. Yes. He got, actually Andreas and Alex, they called Valery Yeshuk, hi Valery, and myself, and said that there is very interesting work that we've been doing in collaboration with John Clark, trying to look at NMR at very small fields, but maybe atomic magnetometers also could be used, and we would like to discuss with you. And I should say, Valery and I were quite skeptical about this, but we went to talk with Andreas and Alex, and that was the beginning of a new chapter in our lives, I would say. Anyway, I should say that chemists, I think, understand NMR better than physicists, and somehow, and so we found, my group members and I found that we need to explain in physics language what the zero field NMR is. So my postdoc Michael Ledbetter and I, we wrote this little article for Physicists in Physics Today a few years back. The thing is, if you tell somebody that you want to do an NMR without magnets, they would probably refer you to a doctor very quickly, because NMR requires normally magnetic field not once but 3 times. So you need magnetic field to polarize the nuclei. Then you need the magnetic field to somehow encode whatever you want to study. If it's imaging, you need you want to know where the spins are, so you need field gradients to sort of locate the spins. And then in a normal NMR machine, the NMR signals are detected by Faraday induction. So you put the spins perpendicular to magnetic field, they precess, you put a pickup coil, and you measure the voltage on the coil, which is by Faraday law d phi dt. So this time derivative is actually omega, Larmor precession frequency, so it's another power of magnetic field. So no matter how you look at it, it would seem that at least B squared is sort of the figure of merit or something like this. And in fact, this is sort of a traditional direction in NMR, bigger and bigger magnets. So the idea of having an NMR without magnets is just to get rid of the need for magnets on all of the 3 stages. And let me quickly walk you through this. So first, polarization. So normally it's done, you put the nuclei in the magnetic fields and they polarize thermally. But I already mentioned this laser polarization technique, hyperpolarization of xenon, for example, that can provide you much higher degrees of polarization. And there are other tricks that are very effective. For example, parahydrogen-induced polarization. I'll mention that in a second. I should tell you that being a very lazy person, my favorite way of polarizing the nuclei is do nothing. Actually, it's my favorite method for anything else also. So the idea is that if you have a bunch of spins, say n spins, then if you prepare them randomly, there will be a square root of n excess in one direction. You can use it. It's called noise spectroscopy. People use it all the time. The beauty about noise spectroscopy is that as you reduce the sample, make n smaller and smaller, at some point you have just one spin, and for one spin, square root of n is equal to n. And you might say, this is science fiction, but in the end of my talk, I'll tell you this is reality. People already do this. All right, so for encoding of useful information, I already mentioned that there are two big directions. There's imaging and spectroscopy, and I should say that the zero field games are played in both imaging and spectroscopy, but let me focus on spectroscopy. And the goal of spectroscopy is somebody gives you some chemical or some stuff, and you have to determine what it is. So what is the chemical environment? And usually this is done by the effect called the chemical shift. And this is usually a very small difference in the magnetic field that the spins see depending on the chemical environment. And you know, the unit in which officially the chemical shifts are measured is a funny unit. It's ppm, parts per million, because the effect is very small. It's typically maybe 10, in some cases maybe 100, 1,000 is very, very large. So it's tiny relative shifts. So you go change, you know, ethanol to methanol. One is good for your health, another one kills you, and it's a few ppm different. But there is another effect that I'll describe, which is Jcoupling. And as you will see, when you go from one chemical to another, you get completely 100% different shift. So let me tell you now what Jcoupling is. And as I already said, almost anything in NMR was invented by Irving Hahn or discovered by Irving Hahn, including this effect. Actually, this one was discovered independently and essentially simultaneously by Charles Lichter and Irving Hahn. And the effect is the following. So imagine that you have a molecule with two nuclear spins, let's say a diatomic molecule or something. Then these two nuclei have magnetic moments, and you have a dipole-dipole interaction, and this is a classical expression for dipole-dipole interaction. Then say you're dealing with liquid or gas. Now, liquid or gas, the molecule tumbles like crazy, very, very fast, much faster than the time scale associated with this energy. And this normally leads to complete averaging of the dipole-dipole interaction. And so it was quite a shock to these gentlemen when they did some experiments, and they saw, no, it doesn't completely average. And in fact, there is an interaction that looks like I1 dot I2, so this spin-spin interaction part, but without this annoying 1 minus 3 cosine squared theta that averages. And the effect is very small. It's typically maybe 10 hertz, 100 hertz, in exceptional cases maybe a kilohertz, but it's there. It's discovered. And you might wonder where it is coming from, and I can tell you, especially for atomic physicists in the audience, that this is a second-order hyperfine interaction. So one spin talks to the electrons that are close by and mixes electron states, and then the electrons are sort of long distance, they're everywhere in the molecule, and then they go and talk to the other nucleus, and this way there is an indirect sort of second order hyperfine shift that occurs. All So that's what we use. And the nice thing about it, even though you can use Jcoupling at high magnetic field, you don't need to. It also works very nicely at zero field. In fact, right now, we are starting to exploit the fact that at zero field, the Jcoupling is different. There are components in this, there's Jonathan King somewhere here in the audience who is the biggest master of this particular topic. You can ask him questions later about this. Then the final reason that in normal NMR we need a strong magnetic field is detection. But here, John Clark showed us how to do this. We use another kind of magnetometer that doesn't rely on Faraday induction. And this is split, and in our case, it was an atomic magnetometer. So you put this all together, and you convince yourself that you might have some kind of an NMR without magnets, but does it really work? Well, let's see. Before I tell you about those results, I need to give, I'm sorry, to those who know, I need to give a little tutorial on parahydrogen. The use of parahydrogen in NMR was pioneered by these two gentlemen. I think Tim Bowers was actually a postdoc in the Pines group at one time before the discovery, so there's a connection. Anyway, this is parahydrogen 101 for you. Hydrogen molecule has two nuclei. Both protons have spin 1/2, and so you can have, when you add two spin 1/2s, you can get spin 0, that's parahydrogen, and you can get spin 1, that's orthohydrogen. And the energy of this interaction is actually not so big. It's a dipole interaction. But we should remember quantum mechanics. The hydrogen atoms are bosons, and so when you permute the two atoms, the wave function has to be overall symmetric, and the behavior with respect to this permutation is dependent on the kind of rotational state. And so you have this very tiny, I would say negligible spin-spin interaction, but the spin state dictates what kind of rotational number you can have. And we here graduate to parahydrogen 102 already. So now the spin determines actually the rotational state, and the distance between the two lowest rotational states in parahydrogen corresponds to something like 175 Kelvin or so. So it means that if you take a bottle of hydrogen and you cool it already to liquid nitrogen, it's polarized to 50%, which is very, very high. And if you can afford to go lower, it's 99.9% at 4 Kelvin. And there are some little details you need to put. The conversion times could be very, very long, so you need to put some catalyzer or something. But nevertheless, it's easy to make fully polarized parahydrogen. And this is spin statistics in action. So now you might say, wait a minute, it's of no use for NMR because I just explained that parahydrogen is spin 0, you cannot see it in NMR. But the trick that you can play is that you can take this parahydrogen and you can have a chemical reaction with some molecule, and when the parahydrogen attaches, the two parts of this entangled state, if you want, find themselves in different locations. They don't have to be equivalent, and they see different things, and that leads to observable effects. Let me illustrate this with a system, a model system where you have one carbon, and that is very close to one of the protons, so these are strongly bound. And then another proton further away, so it's weakly bound. So you have basically 3 spin 1/2. So before the chemical reaction happens, you have parahydrogen, and it's all in the singlet state, right? And then the other system well, first of all, let's talk about the strong coupling. Carbon and proton, it could be, again, singlet or triplet. So this is all singlet, and that, if you don't have high resolution here, is another triplet. And the splitting here occurred when you add the last proton to here. And so what you can immediately see, that because you started with spin 0 here, the spin 3/2 that can arise because you have 3 spin 1/2 united together is the biggest one. It's not populated, it's empty. Okay, I don't have time to explain, but the population in this one is 3 times bigger than that. Believe me, it's an easy problem to work out. And then we have this system, and now we do NMR. What do we see? Okay, well, we have this state populated, nothing there, right? So this is transition 1, we have absorption. Then we tune our frequency further. We go from here to here. Here population is 3 times bigger than here. We have stimulated emission. And then we go from here to here and have absorption again. And this all works out beautifully. And so this is how parahydrogen could, in principle, give you observable signals in NMR. What is the time? I'm sorry. Yeah, good, super, perfect. All right, so how do we do this experiment? It's a kind of funny experiment for a physics department. So first of all, this is, remember, zero field NMR. So we start with a magnetic shield. By the way, these weird shapes were designed by Budker, over there. So you have these fancy magnetic shields. They are multi-layer shields. They make sure that the field here is zero, magnetic vacuum, if you want. Then our magnetic sensor is put in the sensor here, and it's typically a rubidium vapor cell, and we use some lasers to polarize the atoms and to read out the precession. Probe scheme, I don't want to tell you about this. Is another whole lecture there. The point is that this is a magnetometer, and then this is a test tube, and we put some chemical here, right? And then we bring a little straw with parahydrogen, and we bubble parahydrogen through this chemical, and the chemical reaction occurs there. So the sequence of events is that we start this experiment, we bubble for some time, typically 10 seconds or something. Then I have to confess, I lied to you a little bit. There is a tiny magnet, which is not really a magnet, it's a coil, and it applies a millisecond pulse, so let's not count it. That's this thing, this is a little thing here. Okay, but it turns out that in this job, in principle, you can get rid of this also, but if you like drop the sample from the high field, you can get rid of it, but we need it here. Okay, and then we turn everything off, and we're again in a complete magnetic vacuum, and the only thing that our magnetometer sees is the signal from the precessing spins in the sample, and we measure this. Now, you're saying, this is not data, this is a cartoon, right? Okay, it's coming. So, in the experiment, we had this beautiful object called styrene, and you notice this double bond here, and this thing here is our parahydrogen. And what it does, it comes close here, and it breaks this double bond, and these two hydrogen attach in different places. And you see, these are not equivalent locations, that's important. This thing is now called ethylbenzene. Yes, you need a catalyzer for this. And then you do our experiment, and you acquire this, and you get this. By the way, this experiment was done with natural abundance molecules, which means that only about 1% of carbons have spin. The other ones are carbon-12 with spin 0. Okay? And then you get the spectrum, and you see this picture. And at first, it looks ugly before you recognize the beauty in this picture. Well, first of all, notice that these carbons here are colored. So these are red in the ring, and this is like CH over there, and you see this feature is due to these carbons. Then the blue one is, you see, CH3 group. For CH3 group, our theory predicts that you should see two groups of peaks. One is J, and the other one is 2J. This is J, this is 2J, and you really see these. And also notice that this ring is a cause of all kinds of perturbations. So if you're at the ring, it's like a very messy spectrum, but if you're far away from the ring, it's a much cleaner spectrum. And this green is CH2, and we expect 3½ J, and it's right there. All right, then what we did, we wrote a paper. The lead on this was a graduate student, Thomas Theis, who was a graduate student of Alex. So then, nature physics likes to have artwork, and that was our artwork. And I'm kind of very happy with this artwork because you might think it's some kind of an abstract painting, but in fact it has everything. It has the entire information about our experiment. Look, it has our styrene, it has our parahydrogen, it attaches, and then the spin order sort of spreads over the molecule. This is our magnetometer, it's a pump and probe beam, everything like in real life, and it's about our signal at J and 2J. So everything is in this picture, so I'm very happy. All right, so you can continue to play games like this. So this is not a parahydrogen experiment, but still a zero field experiment. This is John Blanchard, who is now a postdoctoral fellow at Mainz. He's photographed here in Birch Hall in front of the zero field spectrometer. And in his thesis, he studied the zero field spectra of a series of these aromatic molecules. And for a physicist, I tell you, these look all the same, right? But a chemist will tell you that there are huge differences here. And in fact, we see that these differences occur in the spectrum. So first of all, again, you see CH3, CH, and so on. And you see that if you're close to the ring, the spectrum is complex. If you go far away from the ring, like here, the CH3, this C13 is there. It's a very clean spectrum. But still, you look at this mess here, and you say, guys, this is a very unpleasant technique that you have invented. You know, gives you some messy signals. What's that? Yeah. So let's look a little bit more carefully at that part. So here it is, and here is the experiment, and this is density matrix calculation. This is what we expect to see. Every single feature is reproduced in great detail in here. Now let's look at these things here over there on the right, and let's do them again. And what we see here is that we have NMR lines with about 11 millihertz width, and I think it's pretty good. I see Professor Warren there in the audience. Hi. Do you usually get 11 megahertz lines in high field NMR?
Not unless you have super long-lived agents.
So it's and here it's almost trivial to get that kind of resolution. So anyway, by the way, this is the slide that I put specifically for John, because there's this pioneering 2002 paper where you looked at this trimethyl phosphate. And John Blanchard last week, especially for this occasion, recorded the spectrum at zero field, and you can see he didn't have time to do a millihertz job, so it's still it's a little bit narrow than then, and it's really this was done at a finite field, I believe, and small but finite, and this is really a zero field, and we have 5 lines and so on, so it's some development. Okay, but now let me connect it back to where we started. We realized while we were doing this that this zero field game is also good, potentially good for dark matter searches for the axion-like particles at very, very low masses. And we chose the simplest possible molecules. This happens to be formic acid. It's what comes from ants, I guess. That's why formic acid. And it has a very simple spectrum, and it has very nice coherence properties. This is actually this, if you zoom in. This allows us to extend the sort of range of reach of these NMR experiments looking for dark matter all the way to maybe 10 to minus 16 electron volt, or maybe even further than that. Okay, so I would like to say that it turns out there are many things you can do with the zero field NMR. I don't have time to talk about this business. I'm just going to mention. Remember when people started talking about quantum computers some years ago. So the first system where people sort of started playing these quantum games was liquid state NMR. And here we also have liquid state NMR, but in a very different incarnation, so to say. And it turns out that you can do a lot of things that high field people could do. For instance, in this work that you can find on the archive, we demonstrated that you can have a universal gate set and do all the like modern things like randomized benchmarking and blah, blah, blah. Anyway, and the fact that it's a zero field and that the Jcoupling interaction is not, as NMR people say, truncated by high fields, potentially open possibilities that are not available at high field NMR. All right, so let me now come to the summary of the fundamental physics with weird NMR. So what I told you about is cosmic axion spin precession experiment that comes in two incarnations, CASPEr electric and CASPEr wind. And then I told you the story of zero and ultra low field NMR. And as you can see here, there are things here. I'm really kind of getting out of time here. There are a couple of things that are on the summary, but I didn't have time to tell you. And one of them is something that we call nitrogen vacancy loop. And this is the idea that you can have this single spin spectroscopy that's now possible with nitrogen vacancy centers, and you can combine it with zero field NMR. And I think the prospects here are really mind-blowing, along with various technical difficulties that we have to overcome along the way, but we are working on it. This is a picture actually of single nitrogen vacancy centers. I can tell you more if you like. And then there is another exciting thing that is happening. It's actually times two, because there are two exciting things that are happening in this rubric. Is measuring parity violation with NMR in chiral molecules. But I don't have time to tell you about this. So I have a wicked plan. But I'll tell you about the wicked plan in a minute. Before that, I would like to introduce and thank our group at the Helmholtz Institute and the sponsors. And there was a wonderful thing this summer, because two of my former graduate students from Berkeley, obviously, are now both professors, Derek Jackson Kimball and Jason Stalnaker, came and spent the summer over there. It was amazing. And I also would like to thank folks here at Berkeley. So this is our group. This is Michael Solers, who is here in the audience and who's able technical assistant, sort of helped us move forward for the last 20 years or so, and also a group of really talented young people over there. We have super close collaboration with people we call pine nuts, and the origin of this, apart from the second part, is that comes from the name pines, right? Pine nuts. So. Okay, and now my weird plan is I'm out of time, but I haven't told you even half of what I wanted to tell. So I have some suggested questions. In fact, to make things easier for you, I even numbered them like this. So, yeah, please, if you like, you can ask me those questions. The last one, I can already give you a partial answer to what is physics on your feet. My partial answer is this. There's another part to this answer. Thank you.
I think we have time for 3 or 4 US questions.
Number one. So what about parity violation in chiral molecules? Thank you. You know, atomic parity violation has been detected already for a long time, but parity violation in chiral molecules, or any molecule for that matter, still remains a challenge. People haven't seen it. Now, in chiral molecules, there's a very interesting thing that happens. All energy states should be dependent to first order on the weak interaction matrix element. This is not the case for atoms, for example. And you might ask, what's going on here? Why do chiral molecules have first order parity violating energy shifts and atoms don't? And maybe anybody knows? Oh, Professor Harris knows. Yeah, but that's because a chiral molecule is not actually a pure parity state. It's a mixture. A real parity state would be a coherent superposition. And in fact, people had a lot of misconceptions. For example, about how come you pour your tea, it's chiral, and in principle there should be oscillation into the opposite chirality, and why doesn't that happen? And actually, it's Professor Harris who figured it out, really, who really explained what's going on there. Anyway, why not to measure an NMR? So we can put chiral molecules in a spectrometer. We can put, now go to high field NMR, 20 Tesla NMR, and start measuring shifts, and we can find a very special molecule with heavy atoms where the shifts will be about 1 millihertz. It should be, in principle, measurable. But you quickly realize that if you have one chirality you measure, and then you take another sample of the opposite chirality measure, things happen. Magnetic field changes, your container has different shape. You can never do this. No. And if you mix them up, you always have this situation where you cannot resolve the spectral lines. You just will be deeply inside the line width. And so there is a project that went on for some time with undergraduate, now graduate student from Southampton, James Ailes. And the idea is that if you take chiral molecules and you have a chiral solvent also, then there should be parity conserving shifts that would distinguish the energies between these states. In fact, what you can do is you can take sort of some molecule and put it in a solvent that is achiral or has equal mixtures of this left and right solvent molecules, and you see just one line. But if you have chiral solvent, you see these two different lines. And then what you can do, again, a strange thing for a physicist, right? You start with a solution where the solvent, where you have a racemic equal mixture of two opposite molecules you want to measure parity violation in, and a chiral solution. And then you see the lines are split like this. And then you take the opposite chirality molecule and you start titrating it, add a little bit of the opposite chirality. And you titrate, you go through 0, and then you see that you have the splitting on the opposite side. And then you can plot plot this energy shift as a function of chirality, and in principle, parity violation shows up as a non-zero intercept over there. But how do you measure the chirality of the solvent precisely? That's a hard problem also, and very subject to a lot of systematic. Well, we use a commagnetometer trick. So in the molecule that we study, we have a heavy molecule that has large parity violation effect, and we have a proton that has small parity violation effect. And so all we need to do is plot the splitting in the molecule with large parity violation effect versus the proton splitting, and then we're done. And so it's a built-in commagnetometer, and the bottom line of this story that I'm telling you very quickly, that this allows to measure parity violation in racemic mixture, and it has a built-in commagnetometer, and we looked at the systematics and they look tractable, and now we are in the process of obtaining the proper, oh yes, I forgot to say, we also did an experiment with a molecule where we do not expect large parity violation, but we have obtained the resolution and so on at the necessary level, and now we are making the good molecule. And so this is one approach, and another one which is even more interesting, and I already mentioned Jonathan is spearheading this, Jonathan King, but I don't have time to tell you about it. But one thing I'm going to tell you about it, uses zero field on the mark, okay? All right, okay. Yeah, okay.
We have just one more question. If you have a suggestion, which question we should ask?
Me?
Yes.
No. Yes.
Would there be an advantage to building two magnetometers, one with each of two of your grain molecules, and then looking for correlations in those networks?
Yes, maybe, but it doesn't solve the problem. Okay, so you will have different, say, the shape of the container would be slightly different, and you will just always see different things. But it's good to, if you do experiment in one system, it's good to try it in another, but it's not, it's not the key. There's one question that has a video, but maybe it'll take time to get to the internet. It shows this network of magnetometers that you mentioned in the beginning, and how the main wall comes through and triggers different. Okay.
One last question. Or two.
Okay. Thank you for that. So I told you how two of my students came to mind this summer, but also one of my teachers came to mind this summer. Yes. So, and his name is Professor Dmitry, and he is a plasma physicist who worked for the last 20-something years at Lawrence Livermore, and this year he won the Maxwell Prize for Plasma Physics of the American Physical Society. And he came to visit Mainz for a month, and so we wanted to find a problem of mutual interest, and the problem of mutual interest turned out to be dark matter. And he had an idea. So one of the things that he did, actually not as his day job at Livermore, but for fun, and the result of that work you can find in the particle data group. In the limit for photon mass, you see that the current limit for the photon mass is less than 10 to minus 18 electron volt, and it's attributed to him. And the way he attributed, the way he figured out this mass limit is there are very precise measurements of plasma in the solar system, because there are spacecraft that go there and measure all the details. And if a photon has mass, your Maxwell's equations have to be modified, and they become Maxwell-Prokop equations, and that leads to observable consequences. And because these consequences are not observed, he set this very, very strong limit. So the idea for this work that is mentioned here is that galaxy is a good conducting medium. There is a lot of ionized gas, and if a photon has finite mass, we can again take the Maxwell-Prakash equations and see what the plasma physics consequences are. So this is done in this preprint, and the numbers come out that you need about 10 to minus 5 of the mass of the current equal to current limit of the photon. So 10 to minus 3 electron volt, and not 10 to minus 18 as the limit. In order to produce forces on the plasma that are of sufficient magnitude to affect the rotation curves at the level, at least, of the magnitude that would be needed. Now, there are a lot of details to be worked out, and of course, once we got this result, the first person we contacted was Professor Marquis, who immediately had a beautiful suggestion for us to look at certain observations, and this is still sort of work in progress, but the bottom line is that at least maybe this is like a baby idea. It's not in any way complete, but it's something that maybe is interesting to look at as an alternative. So that's where it is.
Thank you.
So, yeah.